Hello everyone, welcome back to the channel. This is Mohit Gowda, wearing the USN 1V21 CS 101 from the Department of CSC. Today we are going to learn about automata theory and compiler design. So in automata theory and compiler design, we are going to learn about non-deterministic finite automata, that is the NFA. So now the introduction to non-deterministic finite automata. Non-deterministic finite automata are theoretical models of computation that can be in multiple states simultaneously. They are used in various fields, including computer science and electrical engineering, for pattern matching and lexical analysis. So now, let's look at the definition and characteristics of the non-deterministic function, that is the NFA. A non-deterministic finite automata, the NFA, can have 0, 1 or multiple transition corresponding to a particular symbol. It is used to define to accept the input if there exists some choice of transitions that cause the machine to end up in an accept state. So now the characteristics. Flexibility. NFA allows multiple transitions from a state on the same input symbol, offering more flexibility than deterministic finite automata. Non-determinism. It can transition to one of many possible states for a given input and its transition function is not deterministic. Acceptance. An NFA can accept strings that do not precisely match the defined pattern, providing a wider range of acceptance possibilities. So now, the comparison between NFA and DFA. DFA is deterministic finite automata. So the difference between both are complexity, acceptance power, and transition structure. First, the complexity. The NFA is a typically more complex due to its non-deterministic nature and multiple possible transitions. Uh, Second, acceptance power. An NFA has more acceptance power than a DFA, as it can accept more language inputs. Transition structure. NFA allows empty or multiple transitions on the same input, while DFA has a single unique transition per symbol. So now, let's look at an example of an NFA with transition diagram. First, state A. Initial state with transitions to states B and C on input 0. Second, state B. Transition to state C on input 1. Third one, state C. Accepting state with self-loop transition on both 0 and 1 inputs. So, a question is present. Design a NFA for the transition table as given below. So, the table is as follows. There are 4 states. The initial state Q0, then Q1, Q2, and the final state Q3. 0 and 1. From Q0, 0 is present in Q0 and goes to Q1. Then 1 is present in Q0 and goes to Q2. From Q1, 0 is gone to Q3 and 1 is not gone anywhere. So it will be empty. Q0 to 0. Q0 to 0 is Q0 comma Q3 and to 1 it is Q3. Q3 to 0. The self loop is given, so it will be Q3 for 0 and 1 as well. So now looking at the table, we write a transition diagram. By looking at the table, the transition diagram can be drawn by using the mapping functions as given in the table. The initial state Q0. A self loop 0 and 1 is given according to the table. Then from Q0, a 0 is given to Q1. Then a 1 is given to Q2. Then from Q2, a self loop 0 is given and 0 and 1 is both given to Q3. From Q1, 0 is given to Q3. Then In the final state Q3, 0 and 1 is given as a self loop. Now looking at the transition diagram, uh, uh, the following steps are written. Transition Q0 to 0. Q0 to 0 is equals to Q0 comma Q1 as 0 is passed to Q1 and the self loop is given to Q0. Then Q0 comma 1, that is equals to Q0 comma Q2 as 1 is passed to Q2 and the self loop of 1 is given to Q0 itself. Then the same is done for Q1. Q1 comma 0 is equals to Q3. Then Q2 comma 0 is equals to Q2 comma Q3. Then transition state Q2 comma Q1 is equals to Q3. Then transition state Q3 comma 0 is equals to Q3. Q3 comma 1 is equals to Q3. So this is one of the examples for NFA. So now let's take a look at the NFA to DFA conversion algorithm. Subset computation. Identify the E-closure of the initial state in the NFA to form the initial state of the DFA. Transition function. Determine and implement transition functions for the newly generated DFA states based on the NFA transition. State acceptance. Map the NFA accepting states to the DFA and signify the final or accepting states in the newly formed DFA. Now, the subset construction method. The initial state. Create the initial state of the DFA by computing E-closure of the initial state in the DFA. Second, the transitions. Construct transitions between the newly created states in the DFA based on the NFA's transition functions. Third, accepting states. Designate accepting states in the DFA corresponding to the NFA's accepting states and their E-closure. Let's take an example of NFA to DFA conversion. First, the NFA states. Initial NFA states and transitions for the given example. Second, DFA states. Step-by-step creation and expansion of DFA states from the NFA, along with transitions. Third, final DFA. Complete transition diagram of the converted deterministic finite automata. So, what are the applications and uses of using NFA? Lexical analysis. NFA is used in the analysis of sources code to identify keywords, operators, and other tokens in programming languages. Pattern matching. It is widely employed in text searching, algorithms, and regular expressions. Matching due to its expressive power. Modeling complex systems. NFA can model complex systems, including network protocols, workflow processes, and decision-making algorithms. Now, what are the limitations and challenges of NFA? Non-determinism. The non-deterministic nature of NFAs can introduce ambiguity in language acceptance and complicate algorithmic implementations. State explosion. Transforming NFAs with the high number of states into equivalent DFAs can lead to a significant increase in state of transitions, causing computational challenges. Algorithm complexity. Creating efficient algorithms for NFA operations, including conversion and optimization presents computational complexities. So finally, the conclusion and key takeaways. First, key concepts. Understanding of NFA characteristics, conversions, application and limitations, and also some examples. Algorithmic skills. Enhanced ability to analyze, design, and implement algorithms related to finite automata models. Third, theoretical foundations. Dependent knowledge of theoretical computer science and its practical implications in various domains. So that's it from today's video about non-deterministic finite automata in automata theory and compiler design. Please do like the video. Thank you.